Alright, so in this video I'm gonna be explaining another important article about domain adaptation. The title is a bit more Bayesian, domain invariant learning with uncertainty. This paper in 2021. Domain generalization is challenging due to domain shift and uncertainty caused by the inaccessibility of target domain data. In this paper, we address both challenges with probabilistic framework based on variational Bayesian inference by incorporating uncertainty into neural network weights. We couple domain invariance in a probabilistic formula with the variational Bayesian inference. This enables us to explore domain invariant learning in a principled way, specifically with derived domain invariant representations and classifiers which are jointly established in a two-player Bayesian neural network. We empirically demonstrate the effectiveness of our proposal on 4 widely used cross-domain visual recognition benchmarks. Ablation studies validate the synergistic benefits of our Bayesian treatment when jointly learning domain invariant representations and classifier for domain generalization. As I said, in domain generalization, we don't even have access to any kind of target samples because the target is also unknown. So we have D, a set of domains, and S and T denote source and target domains. Of course, in general, we say that the target domain is unknown, but we can say that there is some T, some target. So S and T do not have any overlap besides sharing the same label space. So this article is one of the rare articles that, although they use the term domain generalization, but they are still talking about a specific target. But we know that in domain generalization, the target is unknown. It could be anything. So we aim to learn a model f from x to y in the source domains and generalize as well to the target domains. But they are very general. They say target domains. It could be anything. We address domain generalization in a probabilistic framework of Bayesian inference by introducing weight uncertainty into neural network. To be specific, we adopt a variational Bayesian inference to learn a neural network that is assumed to be parameterized by weight theta with a prior distribution P of theta, this prior distribution, and the posterior distribution P of theta conditioned on x and y. And x and y are just samples from source domains. To learn the model, we seek for a variational distribution to approximate P by minimizing the Kullback-Leibler divergence between Q and our prior. And also we have a task at hand. So Cristiati showed that applying Bayesian approximation to last layer can effectively capture model uncertainty. So illustrative contrast between deterministic invariance, which is on the top, and the probabilistic invariance, which is on the bottom. You see in this figure that the deterministic invariance tends to minimize the distance between the two deterministic samples. The samples come from their respective distributions, but with limited distributional awareness. So consider this example, a rotation domain in a rotated M-list. D is rotation domain space containing images rotated by continuous angles from 0 to 2 pi a sample from domain can be transferred to a different domain because we go from one angle to the other angle. Zeta is drawn from a uniform distribution. But what is the definition of domain invariance? If x sub I is a given sample from domain d sub I in the domain space, and x be a transformation of x sub I in another domain, d sub z from the same domain space denote the output distribution of input x with model theta. Model theta is domain invariant if this holds. So if the probability of the label condition x is the same. So this zeta is from the same domain, is another domain from the same domain space. So to adopt the domain invariant principle in the variational Bayesian inference framework, we formulate this relation into an expectation from with respect to q zeta. So we use the Kullback-Leibler divergence between the two terms again, but this time we are using this expectation to quantify the domain invariance. And we know we derive this upper bound of KL divergence, which can be approximated by Monte Carlo sampling. So for the classifier with parameter psi and input feature z, the probabilistic domain invariant property is represented as this expectation. As the KL divergence is convex, we can extend it to this upper bound. Which is tractable. The reason that we need this upper bound because the upper bound is tractable with unbiased approximation by using Monte Carlo sampling. In practice, we estimate the expectation over Q in an empirical way. Specifically, in each iteration, we choose one domain from the source domains as the meta-target domain, and the rest are used as the meta-source domains. Then we use a batch of samples from each meta-source domain in the same category as x sub t to approximate x. Thereby, the domain invariant classifier is established by minimizing this to obtain domain invariant representation with feature extractor phi. We extended quantification of our probabilistic domain invariance. This phi, we want to quantify that into this expectation based on Bayesian layer. The probabilistic distribution of features will be factorized Gaussian distribution if the posterior is as well. The posterior of activation Z is also a factorized Gaussian. So it's a factorized Gaussian. So mu sub ij and gamma is just a linear combination of them. This z sub j is the jth element in Z. X sub I is the ith element in X. So in this definition, phi sub ij denotes the element at position ij in phi. So we estimate the expectation over Q empirically. Therefore, the domain invariant representation are established by minimizing this sum of KL divergences. And this is the objective function. But when implementing our Bayesian invariant learning to increase flexibility of a prior distribution in our Bayesian layer, we place a scale mixture of two Gaussian distributions. So the subfigures have the same experimental setting as the experiment table 1 and 2 to obtain more obvious contrast. We use different colors to different categories. The target domain is art painting. So they fix their target domain. Although in domain generalization, we usually don't fix it. We say that each time a new target could be discovered.